Throughout history, humankind has struggled to understand the fundamental workings of the material world. We've endeavoured to discover the rules and patterns that determine the qualities of the objects that surround us, and their complex relationship to us and each other. Over thousands of years, societies all over the world have found that one discipline above all others yields certain knowledge about the underlying realities of the physical world. That discipline is mathematics. I'm Marcus de Sautoy, and I'm a mathematician. I see myself as a pattern searcher, hunting down the hidden structures that lie behind the apparent chaos and complexity of the world around us. In my search for pattern and order, I draw upon the work of the great mathematicians who've gone before me, people belonging to cultures across the globe whose innovations created the language the universe is written in. I want to take you on a journey through time and space and track the growth of mathematics from its awakening to the sophisticated subject we know today. Using computer-generated imagery, we'll explore the trailblazing discoveries that allowed the earliest civilizations to understand the world mathematically. This is the story of maths. Our world is made up of patterns and sequences. They're all around us. Day becomes night. Animals travel across the earth in ever-changing formations. Landscapes are constantly altering. One of the reasons mathematics began was because we needed to find a way of making sense of these natural patterns. The most basic concepts of maths, space and quantity, are hardwired into our brains. Even animals have a sense of distance and number, assessing when their pack is outnumbered and whether to fight or fly, calculating whether their prey is within striking distance. Understanding maths is the difference between life and death. But it was man who took these basic concepts and started to build upon these foundations. At some point, humans started to spot patterns, to make connections, to count, and to order the world around them. And with this, a whole new mathematical universe began to emerge. This is the River Nile. It's been the lifeline of Egypt for millennia. I've come here because it's where some of the first signs of mathematics as we know it today emerged. People abandoned nomadic life and began settling here as early as 6000 BC. The conditions were perfect for farming.
The most important event for Egyptian agriculture each year was the flooding of the Nile. So this was used as a marker to start each new year. Egyptians did record what was going on over periods of time. So in order to establish a calendar like this, you need to count how many days, for example, happened in between lunar phases, or how many days happened in between two floodings of the Nile.
Recording the patterns of the seasons was essential not only to their management of the land, but also their religion. The ancient Egyptians who settled on the Nile banks believed it was the river god Hapi who flooded the river each year. And in return for the life-giving water, the citizens offered a portion of the yield as a thanksgiving. As settlements grew larger, it became necessary to find ways to administer them. Areas of land needed to be calculated, crop yields predicted, taxes charged and collated. In short, people needed to count and measure. The Egyptians used their bodies to measure the world, and it's how their units of measurement evolved. A palm was the width of a hand, a cubit an arm length from elbow to fingertips. Land cubits, strips of land measuring a cubit by 100, were used by the pharaoh's surveyors to calculate areas.
There's a very strong link between bureaucracy and the development of mathematics in ancient Egypt. And we can see this link right from the beginning, from the invention of the number system, throughout Egyptian history, really. For the Old Kingdom, the only evidence we have are metrological systems, that is, measurements for areas, for length. This points to a bureaucratic need to develop such things.
It was vital to know the area of a farmer's land, so he could be taxed accordingly. Or if the Nile robbed him of part of his land, so he could request a rebate. It meant that the pharaoh's surveyors were often calculating the area of irregular parcels of land. And it was the need to solve such practical problems that made them the earliest mathematical innovators. The Egyptians needed some way to record the results of their calculations. Amongst all the hieroglyphs that cover the tourist souvenirs scattered around the city of Cairo, I was on the hunt for those that recorded some of the first numbers in history. They were difficult to track down. But I did find them in the end. The Egyptians were using a decimal system, motivated by the 10 fingers on our hands. The sign for 1 was a stroke, 10 a heel bone, 100 a coil of rope, and 1,000 a lotus plant.
Yeah, how much is this t-shirt? 25. 25? Yes. So that would be 2 knee bones and 5 strokes. Yes. So you're not going to charge me anything up here?
Here, 1 million.
1 million?
Oh my God.
No.
Is this 1 million?
1 million. Yeah, that's pretty big.
The hieroglyphs are beautiful, but the Egyptian number system was fundamentally flawed. They had no concept of a place value. So 1 stroke could only represent 1 unit, not 100 or 1,000. Although you can write 1,000,000 with just 1 character, rather than the 7 that we use, if you want to write 1,000,000 minus 1, then the poor old Egyptian scribe has got to write 9 strokes, 9 heel bones, 9 coils of rope, and so on, a total of 54 characters. Despite the drawback of this number system, the Egyptians were brilliant problem solvers. We know this because of the few records that have survived. The Egyptian scribes used sheets of papyrus to record their mathematical discoveries. This delicate material made from reeds decayed over time, and many secrets perished with it. But there's one revealing document that has survived.
The Rhind mathematical papyrus is the most important document we have today for Egyptian mathematics. We get a good overview of what types of problems the Egyptians would have dealt with in their mathematics. We also get explicitly stated how multiplications and divisions were carried out.
The papyri show how to multiply 2 large numbers together. But to illustrate the method, let's take 2 smaller numbers. Let's do 3 times 6. The scribe would take the first number 3 and put it in one column. In the second column, he would place the number 1. Then he would double the numbers in each column. So 3 becomes 6, and 6 would become 12. And then in the second column, 1 would become 2, and 2 becomes 4. Now here's the really clever bit. The scribe wants to multiply 3 by 6. So he takes the powers of 2 in the second column, which add up to 6. So that's 2 plus 4. Then he moves back to the first column and just takes those rows corresponding to the 2 and the 4. So that's 6 and the 12. He adds those together to get the answer of 18. But for me, the most striking thing about this method is that the scribe has effectively written that second number in binary. 6 is 1 lot of 4, 1 lot of 2, and no units, which is 1, 1, 0. The Egyptians have understood the power of binary over 3,000 years before the mathematician and philosopher Leibniz would reveal their potential. Today, the whole technological world depends on the same principles that were used in ancient Egypt. The Rhine Papyrus was recorded by a scribe called Ahmes around 1650 BC, and its problems are concerned with finding solutions to everyday situations. Several of the problems mention bread and beer, which isn't surprising, as Egyptian workers were paid in food and drink. One is concerned with how to divide 9 loaves equally between 10 people, without a fight breaking out. I've got 9 loaves of bread here. I'm going to take 5 of them and cut them into halves. Of course, 9 people could shave a 10th off their loaf and give the pile of crumbs to the 10th person. But the Egyptians developed a far more elegant solution. Take the next 4 and divide those into thirds. But 2 of the thirds I'm now going to cut into fifths, so each piece will be 1/15. Each person then gets 1/2 and 1/3 and 1/15. It's through such seemingly practical problems that we start to see a more abstract mathematics developing. Suddenly new numbers are on the scene, fractions, and it isn't too long before the Egyptians are exploring the mathematics of these numbers. Fractions are clearly of practical importance to anyone dividing quantities for trade in the market. To log these transactions, the Egyptians developed notation which recorded these new numbers. One of the earliest representations of these fractions came from a hieroglyph which had great mystical significance. It's called the Eye of Horus. Horus was an Old Kingdom god, depicted as half man, half falcon. According to legend, Horus's father was killed by his other son, Seth. Horus was determined to avenge the murder. During one particularly fierce battle, Seth ripped out Horus's eye, tore it up and scattered it over Egypt. But the gods were looking favourably on Horus. They gathered up the scattered pieces and reassembled the eye. Each part of the eye represented a different fraction, each one half the fraction before. Although the original eye represented a whole unit, the reassembled eye is 1/64 short. Although the Egyptians stopped at 1/64, implicit in this picture is the possibility of adding more fractions, halving them each time, the sum getting closer and closer to 1, but never quite reaching it. This is the first hint of something called a geometric series, and it appears at a number of points in the Rhine Papyrus. But the concept of infinite series would remain hidden until the mathematicians of Asia discovered it centuries later. Having worked out a system of numbers, including these new fractions, it was time for the Egyptians to apply their knowledge to understanding shapes that they encountered day to day. These shapes were rarely regular squares or rectangles, and in the Rhine Papyrus we find the area of a more organic form, the circle.
What is astounding in the calculation of the area of a circle is its exactness, really. How they would have found their method is open to speculation, because the texts we have do not show us the methods how they were found.
This calculation is particularly striking because it depends on seeing how the shape of the circle can be approximated by shapes that the Egyptians already understood. The Rhine Papyrus states that a circular field with a diameter of 9 units is close in area to a square with sides of 8. But how would this relationship have been discovered? My favourite theory sees the answer in the ancient game of Mancala. Mancala boards were found carved on the roofs of temples. Each player starts with an equal number of stones, and the object of the game is to move them around the board, capturing your opponent's counters on the way. As the players sat around waiting to make their next move, perhaps one of them realised that sometimes the balls fill the circular holes of the Mancala board in a rather nice way. He might have gone on to experiment with trying to make larger circles.